Suppose you had a problem that was 100 yards long, and the faster you could go from the start to the finish, the faster you could divert the outbreak of a deadly plague, or find ways to combat global warming, or build a lighter, faster plane. Or imagine, when you crossed the finish line, you would understand a complex biological process so well you would be able to cure disease or even extend life itself. Well, right now, corporations, universities, and governments from around the world are lining up for the race of the century. It's a race to solve some of the most complex problems anyone has ever considered. And being first across the finish line can mean not only who gets rich and who doesn't, but who lives and who dies. Imagine a traveler from Hong Kong who steps off a plane in Los Angeles and coughs. And suppose he has avian flu. How quickly do we realize people are getting sick? How fast does it spread? What do we do? That's the kind of problem that Kai Kadu of Los Alamos National Labs is trying to solve with the supercomputer.
The reason why we need high-performance computing for that kind of modeling is really that we have 280 million people in the computer. They move around, we know where they work every day, we know that they take business trips and vacation trips, and they have to interact with each other. And that takes time. If we were to do it on a desktop, it would take the whole flu season to get the answer. So we definitely need high-performance computing to get the answer fast. If you assume the virus comes from, say, Asia into the country, say it comes into Los Angeles airport, and then we have a bunch of sick individuals, what happens next is probably that it will spread somewhat locally in the Los Angeles area, and then the virus might be detected. If you wait too long, and that's something that's really important, the virus, due to mobility by airplanes, for instance, really spreads fast across the country, which then makes it more difficult to contain the virus. The more high-performance computing power we can get, the more reliable is the answer on who are the most likely first responders in the event of an outbreak. It's kind of like comparable with the way weather forecasting started out several decades ago. If you know more exactly the path of a hurricane, you know exactly, or more exactly, who to evacuate and who not to.
Modeling the spread of a virus is just as complex as modeling a hurricane's path. One of the largest supercomputers studying weather is in Tokyo. It's called the Earth Simulator. Recently, its Director General, Tetsuya Sato, proposed connecting the Earth Simulator to a second supercomputer in a simulation that could examine how vast weather systems, like typhoons, are affected by microscopic changes in, among other things, water vapor.
So when we start from the global simulation, and typhoon is generated near the Philippine islands, and it can propagating toward the Japan islands and growing, and then we pick up lowest pressure part, and we make a formation of clouds and rains by using another computer, and so by giving and getting back informations for between microscopic and macroscopic simulation results, and so we can trace of the trajectory of the typhoon, and also where we can have heavy rains.
When you're simulating something as large as a weather system, it's easy to see how a supercomputer might be necessary. But Fred Streitz needs a supercomputer to model the incredibly small. He wants to understand the behavior of a material at the subatomic level.
A lot of those behaviors are are built into the microstructure of the material. And so being able to control the microstructure will actually control the behavior of the material. This was known back through antiquity. So the reason that samurai blades, for instance, were so sought after and are deservedly famous is because the ancient Japanese soldiers recognized that if you work your metal in a certain way, it comes out stronger, and they were affecting the microstructure of the metal. That's all they were doing. Now, they didn't know why, but they knew that that process produced the result that they wanted. We now know how that all worked. So as a computational material scientist, you're always fighting between two limits. You're always trying to model as large a system as you can to touch base with the experiment, but the theory you have works the most accurately at the very, very small scale, because we can do things like quantum mechanics, which we think is fundamental.
By understanding materials at the subatomic level, we can improve countless products, like safer cars and lighter planes. That's what Juan Alonso is working on at Stanford. New air and space-based transportation systems.
Well, so I teach in the aeronautics and astronautics department at Stanford University, and that means that we're involved in things that fly through the atmosphere and out of the atmosphere. I think the main objective of an engineer is to make the world a better place for humankind through technology and through application of technology. In our case, in the jet engine example, what we're trying to do is come up with a completely different paradigm to design the new propulsion systems of the future. So the direct impact on just normal average people of this work is, I think, threefold. First is lower cost. Lower cost means that you and I fly around for less money. That's great. Second thing is lower emissions and lower noise. So this is the environmental acceptability of everything that we do in engineering. There's always a tug of war between having higher performance and having, on the other hand, better environmental acceptability. And with these new methodologies, we're trying to design new engines that allow us to have the proper trade-off between those two. And then finally, in propulsion, so this is jet engines, we're really coming up with, or trying to come up with new and advanced methods to power the vehicles of the future. What we end up doing is just simulating the world inside of a computer. And it turns out that to do it well, you need very large computers. But what we want that simulation for is not just to find out if we do something, what is it that the airplane or the spacecraft is going to behave like. Rather, what we like to do is to affect the parameters of the design such that we can make that airplane perform better, have fewer emissions, make less noise, be more usable, lower costs, so on and so forth.
One of the most pressing problems is the need for clean, cheap energy. Bill Tang of the Princeton University Plasma Physics Lab is working on a $10 billion experiment called ITER.
This is the International Thermonuclear Energy Reactor. It will be built in France, in Cadarache, France. It's a consortium that involves the governments, if you will, of more than half the world's population. So we have now come to a stage where this particular source of energy is truly on the platform, if you will, on the threshold of having a major impact. And we'd certainly like to accelerate the pace of progress in this area. And the area that I'm involved in particular, involves trying to capture the dynamics of the particles that are trapped by the magnetic fields that will enable this fusion reaction to take place. And the confinement of these particles is a critical issue. You have to keep it around long enough for the reaction to take place and then sustain it. And this is a grand challenge problem.
Using supercomputers to study nuclear reactions has already had a very significant impact on the world.
President Clinton signed an order banning the underground testing of, or the detonation of any nuclear device in the United States. And how could we do that? How can we now go back and ensure the safety, security, and reliability if we couldn't actually test? And the reason he was able to do that is because we had computers powerful enough that we could actually model that process with sufficient accuracy to do our mission, to ensure the safety, security, and reliability of the nuclear stockpile. And that's actually a very tall order if you think about it.
John Bell of the Lawrence Berkeley National Laboratory is looking at more immediate solutions to the clean energy problem, like how to mix hydrogen and oxygen to create the perfect flame, one which produces the most energy with the least emissions.
So one of the things that they would like to do is be able to burn clean coal, and they've designed these cycles in which you can burn clean coal by first gasifying it, but the gas you get out has very high hydrogen content, and it turns out that whenever you look at burning pure hydrogen, which is one of the scenarios they look at, all of the basic theory for how premixed flames work, which is the target for the systems they want to design, all of the theory that they have for understanding experimental data doesn't work. It's all out the window, and they get structures that they observe in the flames that they don't understand and don't know how to analyze. And it's only by doing simulations at very high fidelity and very large scale systems that they can actually understand what they're seeing in the experiments.
High-performance computing is letting us visualize things we've never been able to see before. And according to Chris Johnson, it's helping us answer fundamental questions and understand science at an entirely new level.
One of the things that's happened, I think, recently on the visualization side is the ability to see things at these high resolutions for the first time, and the ability to see them in more of a time-dependent, interactive way, rather than a played-back movie from one viewpoint, has allowed scientists to gain insight that they couldn't get in any other ways. And this is how we progress in science. These are the tools that we've created that open new windows for the scientist to see in new ways. If you look at many, maybe even most of the great discoveries throughout mankind, you'll find that before the great discovery was the creation of a new tool, or a tool that's been used in a new way. And that's really where high-performance computing and visualization, these high-resolution display walls that people are creating, the graphics cards that people are creating, the hardware side, the new algorithms, the software, these are the new tools for these scientists to look at their data and their science in new ways, and will make new discoveries because of it.
Chris says that before most great discoveries comes the creation of a new tool, or a tool that is used in a new way. When we first learned how to make lenses, it changed our view of the world. But it was putting lenses together that really changed things. Suddenly, we learned our own world was more amazing than we'd ever imagined. And with different lenses, we could see whole new worlds. An understanding of optics advanced astronomy, medicine, physics, and chemistry. Optics changed everything. And now the sciences are about to be revolutionized again. This time with supercomputers. Just ask Tony Mazzacappa.
I started working on core collapse supernovae about 20 years ago. So it's been about 2 decades of painful progress. So we're trying to understand how these massive stars explode. They are stars that are 10 times the mass of our sun and more massive. We're trying to understand these stellar deaths because of their role in the cosmos. They are the dominant source of elements in the universe. They are the dominant source of elements between oxygen and iron, and there's growing evidence they're responsible for half the elements heavier than iron. I believe we are currently at the threshold, at least, of a new age of science. I believe we are entering a new age of science, and I believe that because of the advances in computational science generally, in computing power in particular, to model such a multi-physics event requires concomitant computing resources. We could not even think about attacking this problem in all of its glory and all of its richness before. Now, for the first time, certainly within the last 5 years, and I think this will be even more true in the next 5 years, for the first time we can address this problem in all of its glory and really advance the science essentially, in a quantum leap fashion. So that's why I believe that we really are at the threshold, at least, of a new age because of the growth of computational science and the resources on which that is based.
Rick Stevens has a nice way of summing this up.
we're entering a realm right now where there's sort of 4 different strategies that suddenly become possible in high-end computing and large-scale computing that weren't historically possible before. First strategy is to do what I'll call seminal computations or fundamental computations that become resources for many other communities. An example of this would be a high-resolution climate simulation. Another strategy is you've now got enough compute power that you might try to solve a problem that fundamentally alters how a community thinks about something. So here's an example that is in the Department of Energy laboratories is one that's very compelling. So we've never been able to design from first principles a catalyst. Okay, so a catalyst is a molecule that accelerates a chemical reaction. A third strategy is using large-scale computing to mine data. Okay? And a classic example of this is trying to find things in genomes, because we're generating lots of data. Genomes are actually increasing exponentially because sequencing is becoming increasingly inexpensive. The fourth area is one where we're trying to build something that's really complex, but we're trying to do it on a schedule. Okay, again, in the federal government space or international research community, there's a couple of devices that are trying to be constructed in the next few years that fit this bill. One of them is ITER. And the question is, can you optimize the design in the time frame you have to influence the construction schedule? So you've got a finite amount of time, and you have imperfectly understood physics, and you have a very complex device. So these 4 things are what I think tell us that we're on the verge of a golden age, or on the verge of changing the game, and we're changing it not just in one area. It's not like we're changing it just in biomedicine or just in physics or engineering. You're changing it, all these things simultaneously. And then you couple that with the evolution of the web and with the evolution of collaboration technology. So now you have the ability to bring people together quickly, to collaborate on building the software, running the jobs, visualizing the output, iterating through that process. You have a tool that's going to accelerate things dramatically.
I believe the pace of progress has been truly extraordinary and exciting, and puts us on the threshold, if you will, of really capturing the most essential underlying physics that we need to better predict performance in the advanced machines, both the existing ones leading up to, over the course of the next 10 years, to the delivery of this international machine.
And we're really starting to be able to work not only in this particular application, but in many applications where you're taking the best people in computer and computational science and the best people in neurosurgery or physics or whatever it is, and you're working together to solve problems that neither of you could have solved previously. And I think that's where we're at with a lot of different applications, is that we're at this tip of the iceberg where we are going to see a golden age of scientific computing. And specifically for some of the applications we're working in is the applications of computing in medicine, where we're going to be able to transform some of the ways that they do medical imaging and diagnosis and treatment with computing, and it's going to be amazing.
If we can harness these machines, there are a lot of areas that we can make a big difference in. Combustion is one, the astrophysics problems I mentioned is another. There are a lot of things that are still going to be really intractable, but yes, you can start to see this making a difference. And the way you start to see the difference is we go from doing little idealized things to be able to do things that are realistic. It is sort of a golden age for science, but it's not a golden age in the sense that now all of our problems are solved. It's more, now we integrate all these pieces that were disparate before. So it's going to be a golden age, but it's also going to be a much faster age. We're shortening that loop. And in the commercial world, what we're doing is we're sort of accelerating the innovation cycle, right? So an innovation cycle is where you have an idea, try something, right? It doesn't quite work,
you fix it, I mean, you're sort of increasing the rate at which you can fail, right? And the idea is that's good because the more failures you can make per second or per hour or per week, the faster it is you can move towards some goal. What the computer does is allow us to fail, at trillions of times per second or something on the way towards achieving some problem or achieving the solution to some problem. So that's why it's so cool, because it touches everything, and at the same time, even the tools and the ideas that are necessary to make the next generation system happen are also accelerating.
A lot of us really feel like we're in this golden age where we've been working up, taking these things that the fastest computers and the best software that we've had, but it really could only do a small portion of what we wanted it to do in terms of addressing the complexity and the needs that we had and answering the questions that we had. And I think we're just getting to this point where we're seeing that we're able to, with the advanced hardware and software and algorithms, that we're starting to be able to answer some of these questions that we've always wanted to answer for the very first time. And we're starting to open windows into discovery that we've never been able to open before. And that's leading us into very new and very interesting places. And I think it's leading to this golden age of where scientific computing is going to change the way we do science and medicine. It feels really exciting. It's great. It makes you want to get up every day and go to work.
Are we on the brink of a golden age of science? Can anyone really imagine the doors to understanding that a miraculous new tool might open? Perhaps we're just finishing the first lap of a supercomputing race that has an unimaginable finish line. One thing we do know, we're beginning to learn how to build and use an extraordinary new kind of tool, the supercomputer. And because of that, the race to what's next is just getting started.
Computers are incredibly fast, accurate, and stupid. Humans are incredibly slow, inaccurate, and brilliant. Together, they are powerful beyond imagination.